Thank you so much for the introduction, Edward. I'm very happy to be here today and welcome everyone to this exciting topic of semantic web and knowledge graphs today. There has been a lot of interest actually, especially as we also have a demonstrator, which is called No Text. It works in the area as well. So if you really want to know more about this, let me know as well. I would be really happy to talk to you about the demonstrator too, which is exploring a lot of the fields that I'm going to talk about today as well. But semantic web as itself, which nowadays is mostly, we're mostly talking about knowledge graphs, but semantic web is really the technology that has been developed in the area for more than a decade now. So let's just start with an introduction of the field and what semantic web actually is. So I'm actually having an anniversary this year because it's 10 years since I started working in semantic web. Quite a bit of time, and there has been a lot of developments in recent years, especially from the industry side, which is very exciting for us in research as well. But if we look at definitions, so from the beginning of the semantic web, which was on the turn of the millennium, it has been defined as kind of an extension of the current web, right? So what we know about the web is that it's huge, that there is a lot of information, but we have some problems with sharing those. If you look at the definition of Webopedia, that tells us this. But also, more specifically, if you look into Wikipedia, how semantic web is defined, you will notice that it talks a lot about machines and machine understanding the web. Sorry, I'm just going to mute everyone so that we don't have any interruptions. There will be time for questions afterwards enough, so no problem with those. Right, so Wikipedia actually has started talking about machine understanding and machine trying to capture the meaning from the web by using some kind of semantics, as you can see here. And then Tim Berners-Lee, who as you probably know, invented the World Wide Web, but also was the person who first started talking publicly about the idea of a semantic web. Also says that we want the web to be processed directly and indirectly by machines, right? So this means that we want to structure information in a way that can be understood, but also reused by machines. And by this definition, semantic web would actually be concurring technology to artificial intelligence or machine learning. Right, so from the beginning of the field, there was quite a discrepancy between artificial intelligence and semantic web, which was very interesting to observe. But later on, also to notice how more and more collaborations started to flourish between machine learning and semantic web as well, as we will see later on. Right, so just about this idea, right? Today's web, as we know, is very easy to read and interpret by human users. So it's very easy for you to browse websites, to use Facebook and so on. So just to read content that's generated mostly out of databases as the web is structured. But then if we really want a machine to understand this, it gets more complicated. Right, so the typical users on the web that we have today is searching for information, right? We're looking at blogs and news and several types of web searches every day. We're using a lot of social networks. So people spend really unbelievable amounts of time on Facebook, Instagram, Twitter, and so on. But also online shopping, which is quite a good use case actually to demonstrate the usefulness of semantic web technologies. Right, so if we look at the problem, right, we have meaning of the content on the web that's not machine understandable, because we have no semantics that can be parsed basically by a machine. So web content is heterogeneous, which means that we have little to no structure. There is mostly just text that we need to browse and understand. And then if you're a human being, it's pretty easy for you to follow links and to crawl from one website to the next. in search of consistent information. But for a machine, this would be very hard because it doesn't really see what those links actually mean that it's following. So the sharing of this data is actually pretty hard as well for content providers, because there are several sources, but they're not really connected. So humans have to gather basically bits of information from several sources, and that is really hard work, right? So if you're trying to find the best flight, for example, for you on a specific date, then you would basically have to find different airlines, compare those, and try to find the best option for you. Whereas if you knew the parameters, it would be pretty easy just to define them and let a machine do that for you if it would be able to understand the semantics behind it. So the vision of the semantic web is some kind of very complex and very meaningful search and extraction of information. So if you think about, for example, Google Knowledge Graphs, so Google is actually a good example because they've been using semantic search for quite a while. A lot of this time, actually, we had no clue about it, but when it surfaced, it became obvious that they have huge data in the structure of a knowledge graph, but it's proprietary, so we don't really know about which technologies they use and how this is structured. Also, Wolfram Alpha search engine, maybe you've heard about that, is a very, very advanced one that uses knowledge graphs under the hood and is able to give you very sophisticated search results and answers to quite complex questions from a mathematical perspective. So this is, if you know the software Mathematica, for example, which is from Wolfram, the company, they have a lot of mathematics-based and physics-based search engine results there. So what we actually want in the semantic web then is web information to be processed by computers, obviously. And we want to integrate this information from the web. So we want needless integration and the possibility basically to do really sophisticated stuff and interesting stuff with the information that's out there. So this actually brings us to knowledge management, right? So knowledge management also has been a topic in companies for decades. So companies have been thinking about how to manage their knowledge, how to organize it, how to make it available to everyone, how not to duplicate documents and information. But knowledge management itself became only interesting after the semantic web came up, because this is when you actually can connect all your knowledge within a graph and make it structured and publish it, share it with others, connect it to other knowledge graphs. So that's the interesting part of it, basically. Right, so it's organized in some kind of conceptual spaces. So we're always looking for a context in which we are looking at information. And then what we want to see is automated tools for knowledge discovery, basically, and also knowledge maintenance. So automatically discovering new knowledge, because we don't want to state the obvious. We want to infer new stuff as well as semantic query answering. So quite complex questions that we basically want to ask the system and get results that exactly tell us what we actually want to know. So we also want to define which parts of documents who is supposed to see and who not. So we want some kind of privilege system as well there. So in e-commerce, what does that mean? We have a lot of typical scenarios, especially with online shops. So just if you think about when you want to buy a very specific thing, like let's say a tool, right? Yeah, and you're trying to compare prices from several online shops. So normally nowadays you would just go to Amazon and buy it there. But what if it's something very specific that you really can't find there, or you really need to compare different products, different types of stuff? You maybe just have a task that you need the right tool for, but maybe you just don't even know what the tool is called, right? So you want to browse in a specific context. In this case, home improvement maybe, And then you want just to have a very complex query that tells you exactly where to buy it and where to get the best offer. Right, so shop bots have been used for similar purposes quite a bit, but they're not really efficient. So they normally work on textual analysis. They would look for keywords. Also, they wouldn't really have a context. And they would have to be reprogrammed every time, right? So every time you do a new search, you would have to change your sources and lots of manual stuff for a search bot to be really efficient. Yeah, so software agents, as we know, they also have specific terms of service. So we need to be sure that pricing and product information, delivery, privacy policies, and so on all match, right? So this is, again, something that would be very easy to do with a knowledge graph if we were connected there. Also reputations of shops, like ratings of different shops and products that you need to browse manually right now, but you could just do an automatic search by telling, you know, I only want to buy products that are rated at least 4 stars and so on. So something sophisticated is really needed there that would improve this shopping agents that have a lot of hard-coded stuff, basically. Right, so if we have a look at such an example use case, what could we do? Let's say you're trying to work on a conversational knowledge graph. So let's say you want to do something like traveling to a specific location or a specific date, and you don't really want to deal with the specifics, right? So let's say you want to travel to New York 2 days before Thanksgiving. So you want to spend Thanksgiving in New York. You want to stay for a week. So we just say that you want to do that. Right? And the system would have to understand what you actually mean by that, right? So we would extract the travel information. We would extract Thanksgiving as a date, and we would need to browse the knowledge graph actually to tell us what day Thanksgiving is going to be. And this is especially interesting if it's, let's say, a holiday that's not on the same day every year. Then we know that you want to go to New York for a week. Right, so we just follow the knowledge graph. If you have a look on the right side, you can see that we find information. For example, the JFK airport is in New York. So if you find a flight there, you would know that this is the right airport for you. And then you come back with a suggestion and say, so the system would answer you, okay, I'm going to book your flight to JFK from November 20 to November 27. And just has to come back and ask you where you're flying from in that situation, right? So knowledge graph would come back asking for more information when it is needed, right? So in that case, you answer that you're flying from San Francisco and that you want a non-stop flight in first class. So we are getting this information again back into the knowledge graph. We find a flight here. That's in that case a Delta 2648 flight. Given the filters that you actually requested, and then come back with the flight suggestion. Then the user again can review the flight that's offered, and then saying, for example, in that case, how about leaving in the afternoon, because that was maybe a too early flight that was suggested. So the system again goes back and adapts the new filters to the search and gives you another option for that flight. Right, so this is the basic, or a pretty good use case that shows you what a knowledge graph could do that improves the state of the art to a simple search on the web, where you would have to compare different flights and look for that all manually. Right, so in order to be able to do that, what we need is linked open data. Linked open data actually means that you're publishing data on the web, and you're trying to do that in a format that enables knowledge graphs, right? So let's say in linked open data, Tim Berners-Lee actually came up with a rating system for your data that you publish on the web. So if you, for example, even publish your data in a form that can be read by others, like a PDF in that case, you would get 1 star. Then you could publish it in a form that's structured, like an XLS file. But this is still a proprietary format because it's a Microsoft format. You would get 2 stars. If you publish in a structured format that's not proprietary, like CSV, so that can be read by different types of software, you will get 3 stars. If you publish it in RDF, which means that you have a graph already, you would get 4 stars. And if you publish it as linked open data, so even linking to other knowledge graphs that are similar, then you would get 5 stars, right? So this is the optimal scenario. And if everyone would follow these principles and publish 5-star data, then knowledge graphs would be really, really easy to do on the web, and all this would be possible. So that's the basic idea behind it. Right, so talking about knowledge graphs, now that we know what semantic web basically is, we're getting to the core of knowledge graphs, which are ontologies, right? So ontologies actually model the knowledge and the semantics part of the whole thing, right? So ontologies tell us actually what this information means in that case. So if you have a look for at an example here, this is an ontology that's used a lot as an example case. So you could, for example, have different classes, very similar to object-oriented programming, where we have here different cuisines, like American and Asian. Then we have subclasses in Asian, like Chinese, Japanese, and Korean, right? So we know that those cuisines are Asian cuisines too. Then we have Mediterranean, for example. And if we then have a restaurant, let's say a Chinese restaurant, then we could say that a Chinese restaurant has cuisine, some Chinese, right? So we know that a Chinese restaurant would prepare Chinese dishes because they have a Chinese cuisine as well. And this is the property has cuisine that makes it able to make this connection between the type of food and the restaurant that provides that. So then going further, we would, for example, know that Chinese, Japanese, and Korean might be similar because they have Asian food. So they might have dishes that overlap or that taste the same, that are maybe spiciness is similar, definitely more similar than something Mediterranean, for example. And then we could query for restaurants that have a specific type of cuisine that we want to see and get very good results connected to that. Okay, so this would give us the meaning basically of what we're actually trying to do here. So when we're going on the quest for semantics, what we actually have to do are basically 3 steps. So we're building a model like this ontology example that we've just seen to allow a machine to understand the context of the part of the world that we're modeling. Then we're computing this knowledge, so we're constructing new connections. We're trying to reason over the knowledge graph and find new information based on the ones that we already modeled, especially when adding instances of that and real data to that model. And then we're exchanging the information, so we're linking to different distributed knowledge graphs that are out there. So we are getting to the open link data principle in order to be able to get a deeper context and more understanding about the topic that we have here. So when we're calculating with this knowledge, so as I said, semantic web and AI were for a long time 2 fields that were fighting each other, basically trying to get better solutions to similar problems. But nowadays we have discovered that the strength lies in cooperation. So the strength is wherever we're trying to combine machine learning and semantic web to get even better results. So the amount of knowledge here basically is quite overwhelming, and research is concentrated a lot into preparing basically machine learning models using semantic web techniques, or using machine learning to produce more complex and better knowledge graphs. So on both sides, there is a lot of work going on right now. And we are also growing the tasks. So the problems are becoming bigger and bigger the more data that we have. So we have a high complexity and size on knowledge graphs, which means that we need to be very scalable as well. So how do we do that actually with a language, right? So exactly like in programming, we need to have a specific language that helps us modeling all these knowledge graphs and ontologies and so on, right? So for this reason, the first language actually that has been introduced is the so-called Resource Description Framework, or RDF, which means that we are trying to represent knowledge in a very natural way, right? So, so basically bringing it down to the core, what we're actually doing is we're mimicking language. So if you have a look at the third bullet point here, it's the most important one actually, which means that we are trying to connect entities, trying to connect nodes in our graph through a subject, predicate, object format. So we are basically using, like in normal English sentences, subject, a predicate, and an object to connect two nodes in the graph. So if, for example, we could say that John is a friend with Bob, which would connect the two nodes, John and Bob, in the graph with a predicate that would tell us more about the relationships between those two. So we have different standards that I'm going to explain as well, but all of them basically are building on RDF. So RDF is the format that we use for knowledge graphs and to construct this graph structure of knowledge that we then want to work on further. Yeah, so just a few examples here. We could say Andrew knows Matt. We could say Andrew's surname is Perez Lopez. We could say Matt knows John. Ryan works with John. So how would this look like in a graph? So if you have a look at this graph, we have those four nodes representing Ryan, John, and Matt, and Andrew, and then connected by predicates. And then we have Perez Lopez as a surname. Right, so if we have a look on that, what it actually means. So in one sentence, the subject might be Ryan, predicate works with, object John. In another, John would be the subject, predicate knows, object Matt, and so on. So those are the resources, the round nodes in the graph. And then the literals that are represented here by rectangles would be standard data types, like in this case, a string. So you wouldn't be able to connect Perez Lopez any further because this is just a value for our resource Andrew, and it's not really a node in our graph. Yeah, so in RDF actually, we would also have to use unified resource identifiers. So every single node and predicate in the graph would have to have a unique identifier that's unique on the whole web, right? So therefore we need complete namespaces. Like in this case, we would need to have a full naming that's unique on the web, ideally linked as well if it's linked to open data, so you could click on it and get more information on it in a browser even for each of those elements in our graph. Yeah, so then what really gets interesting then, and this is also where the fun starts for us in research, is when we start thinking about inferencing, because it's all well if you can connect that in a graph, but what if you're trying to automatically infer new information? So this is where relationships are then added to connect more integrated information. So let's say we have an apple that is also a fruit. So we are expressing this. So every time we actually refer to the apple, we're also referring to a fruit because we know that an apple is a fruit. So based on this, we can infer new information. Or we could say that if a restaurant has a specific location, then this also means that the location itself contains the restaurant. Right, so only one of those two triples is what you need to define, and the other one will be automatically inferred from that information. Right, so this can increase in complexity a lot. So the more complex your graph gets, the more advanced your inference is going to be as well. But from a machine perspective, if you just look at the graphs on the left and the right side, right? So on the left side, it's for a human being, it's quite easy. Sorry, I don't know where those annotations are coming from. But on the left side, you can see that a graph is very easily understandable for a human being. like it's very easy for you to understand what it means if you say Ryan works with John. But for a machine on the right side, what it looks like is just resources connected by properties. It doesn't really mean a thing from an RDF perspective, because we don't have an ontology. We don't know what those resources and properties really mean, right? So what we actually need to do is to give meaning to it. So to attach some schema to that and to be able to tell what it actually means. Very similar actually to XML and XML schema, where XML has random tags that don't mean a thing for a machine. But if you add XML schema and actually define them, it's able to validate it and to represent it in a format that can be understood by the machine itself as well. Right, so we have the vocabulary here that defines all those things, and then those semantic interrelations as well that tell us more about it. Right, and then RDF schema, as I said, adds the actual meaning to the graph. So we are able to tell a machine what the graph actually means and how to make those connections. Right, so for example, here we could have different subclasses of each other, like in that case, books and New York Times bestsellers. And then if we say that Water for Elephants is of type paperback fiction, we could infer that it's a New York Times bestseller. We could infer that it's a bestseller at all, and as well that it's a book, because they're all subclasses of each other. Yeah, so RDFS was the first thing that, the first schema actually that has been introduced there. But then to get more advanced technologies, we also introduced OWL, the so-called Web Ontology Language, that just adds more complexity to RDFS, because we wanted to have more expressiveness. We wanted to have description logic that is more advanced, and we also wanted to have several other functionality on the knowledge graphs that make them easier interpretable, that make them complete as well on the web. So if you're wondering why Web Ontology Language is called OWL, you have just to think about the owl from Winnie the Pooh. So maybe you've read the books or seen the cartoons, but you might have noticed that the owl from Winnie the Pooh always spells itself as WOL, so it misspells its name, and this has been referenced as well in the short name for the Web Ontology Language being OWL. Yeah, so what does it actually bring us? So we have here, for example, expressions that can be done by OWL and were not possible by RDFS, like cardinality. Every project has at least one participant. We could say that projects are always internal or external projects, so we can have restrictions there. We can say that a subgraph is defined by a specific node, like these two people here are secretaries of another person, but also that the superior of my superior is also my superior, which means that we are inferencing information based on subclassing, as we've seen. Okay, so this has been the basic introduction, but what does it mean for industry and research? So the interesting applications here, if we think about knowledge graphs in industry, so we do know that Microsoft and Google, for example, have huge knowledge graphs for their search engines, so Bing and the Google search engine. And they're able to use those for answering questions that are very complex and depend on the context of the user as well, right? So different users on the web will get different results from search engines there. And this is based on the knowledge graphs that they're using. We also know that Facebook, for example, has the world's largest social graph that covers all the information that they gather from users. But also eBay is working on product knowledge graphs, which is pretty interesting. So they're trying to make connections between similar types of products. I guess Amazon as well. And they just didn't make it public yet, how they do it and what exactly they're doing. But also IBM's Watson Discovery has a huge knowledge graph framework behind it as well. So if you have a look here at those facts, you can see the size of those knowledge graphs, like 2 billion primary entities, 55 billion facts for Microsoft's Bing engine, 70 billion assertions for Google, 500 million assertions for Facebook. So those are really, really huge knowledge graphs. They're extremely hard to handle and reason with, but extremely valuable for the companies as well. And they're using those same semantic web technologies that we are working on as well. Yeah, so what challenges do we have actually at the moment? So we have disambiguation of entities. So we want to find connections between entities that are the same and connect them in a form of linked open data. So we want an advanced version of knowledge sharing in the open data field. Then type membership and resolution. So we want to be able to say what type a specific node is of. And compare it to similar types. So we, for example, extracting subgraphs out of your knowledge graph and analyzing those. Then managing changing knowledge. So for example, eBay is using a lot of changing knowledge for their products. So they're constructing a new knowledge graph every time that they are doing a product search on the web. So this is in the beta version at the moment. The knowledge extraction from multiple structured and unstructured sources. So this has been always a problem, how to actually gather data that's not structured or not sufficiently structured and get it in one single knowledge graph representation. Managing operations at scale is, since industry caught up with knowledge graphs, we got a lot of new data in, and it's becoming more and more challengeable to handle all those operations at this huge scale as you've seen for those big companies. Also, semantic embeddings are a topic if you try to combine it with machine learning, right? So we can use knowledge graphs to generate embeddings for a machine learning model and use it there to solve a machine learning problem and improve basically the data quality for machine learning. Inference and verification. So we want actually to find how truthful facts are, which is a huge question at the moment from a political perspective. To be able to quickly verify if information is correct that's provided to you from several sources. Then federation of specific domains, how to integrate domains into a huger or a global scope. Also some security and privacy topics that we're looking at, and multilingual knowledge systems to be able to span over knowledge graphs that are defined in different languages from different countries. On the research side, we are also working on new description logic because we want logic that we can reason with, that's complete, that is very efficient, especially in terms of scalability that we have nowadays. We're trying to work on ontology matching in order to connect different ontologies from different domains, for example, but also data access, especially when we have large-scale processing of RDF data. And how to make information confidential and controlled by having specific queries to evaluate ontologies. And the last thing is for me also a very, very interesting part, that how to combine basically semantic web and machine learning or deep learning nowadays is I think where there is a lot of leverage that we could have in improving products and improving a lot of algorithms and machine learning models that we're using right now. Okay, so just another reminder for our demonstrator no text, where we are exploring a lot of those questions and topics right now. So if you want to get involved with that, let me know, and we could talk about what we're working on there now. Also, we're looking always for use cases and examples, how to basically extend our functionality and specify the end demonstrator as well.